recorded, and you're hearing this for the first time, unfortunately, there's no real color, per se. Hi, that's my hand. Hello. I'll do a little hand puppet thing. Hello. This is E641 and lecture 13. I could have drawn the split on my hand again first. But anyway, so we're picking it up. So unfortunately, I don't have video. I only have the document camera because we're doing this in a different physical venue than normal. So for the off-campus students, I apologize that you can't actually, see me, although I'm not sure that it really changes, quantitatively. Maybe a little bit different human experience. But, yeah, so we'll be doing this. You'll get the audio, and we have the document camera, which goes through the material, but I won't be able to use the Blackboard. And hopefully it should show up on the website, just like it does now. It'll just add to the link at the top. So the actual lecture should appear in order. So let's see. So last time I talked to you, I pointed out that okay, so you have a problem, and it's like the form. Let's use the document camera also. So let's see. So what happens is y equals a times x, right? Huh? Does it look okay? Yes. Plus w, right? Okay, and we want to solve this. Now, and this thing here is normal, mean zero, covariance, inverse covariance, say, minus 1/2 lambda. So actually in the notes, I think I just make this sigma squared times I. Okay. So it's IIT like 1. And then so the max and likelihood estimate. So the NR is I was trying to find x. What I really just want to do is I want to find x. I want R min over x of y minus ax squared. So sometimes this is called pseudo inverse. If a is invertible, then it would just be x hat here would just equal to a inverse y, or not. But it doesn't work very well in many applications. So now a also can be singular. It could be rank efficient. So there's two possibilities when you try to solve a problem like this. The solution may be this, or if the solution may be non-unique, if it could be an infinite number of solutions, or the solution could be non-existent, so that there may be no solution. So it could be that y falls outside of the range of the column space today. Okay? Or it could be that in which case there's no solution. Then there's the so-called pseudo inverse, which is the value of y equals 2 and then we use for her solution. Minimizes this, but it doesn't make it 0. So the solution is may consist of this. It may be non-unique. Okay? So if it's it could be that A has a null space. So if A has a null space, you can always add any member of the null space until the constant, and it doesn't make any difference. So again, the pseudo inverse takes some of those solutions, like, if A has a singular value becomes this, okay, so, it's best not to think of it as eigenvalue, think of it as singular value. Singular value is small, then you have to divide by a very small number to recover that signal in that state. And this is not going to work. So, the map estimate is the case that we're looking at. Is the argmin over x of the combination of the normal y minus ax squared plus, then this is going to be x transpose dx. In this case, well, closed form solution x hat is just a transpose plus b inverse a transpose y. Okay. I'm kind of going from memory here. Right. Now, and in fact, if lambda is in there, then you put a lambda here, and this is actually equal to a lambda over So, now the problem with doing this directly is the computation associated with this conversion is just absurdly large in real applications. You can't do that because these matrices really weak. Their dimension is size number 50 is the image of volume. So inverting is not practical. So instead of the approach, you take a more direct approach, and specifically directly numerically do the minimization. You set up a function f of x is equal to 1 over 2 sigma squared y minus ax squared plus x transpose dx times 1 So take this cost function and you numerically minimize it using various optimization approaches. Very often when you get the optimization, students will say, well, the first thing they'll do is go to MATLAB optimization toolbox. And fine. I guess that's not a bad thing to do in the sense that it shows that you do what you initiate to go on with that plan. But it's often, for a problem like this, it's a really bad approach. Something like MATLAB optimization toolbox will usually work okay. You get a small number of variables, no problem. The dimensionality of this problem is very high. The solving optimization is pretty tricky. And conventional, this sort of blasting conventional method doesn't really work. You have to do something sort of customized and structurally solved. So a pretty standard approach is gradient descent. And the idea of gradient descent is you just move in the opposite direction of the gradient. So if you're trying to solve a minimization problem, so you just take the current value and you modify it by moving in the opposite direction of the gradient. You want to move downward, right? So you compute the gradient of f evaluated with the current value of the function. So you just, and then the problem with gradient descent seems pretty intuitive. The problem with gradient descent is that one problem, actually there's a number of problems, but one problem with gradient descent is you have to pick this dot. So you need to pick this step dot. Okay, and there's a trick on this because if you pick a value that's too large, there's a problem. So let's say we have a cost function like this, right? way up to here, just a quadratic function, right? Then you can get by with it over here. As long as you're over here, as long as you fall in this region, you're okay. But if you go beyond there, up to here, now you're actually now you're actually worse off after the update than you were before you started. So it's a little bit like people who do skateboarding, and you have a skateboard that goes right? Now, if you're a really good skateboarder, I guess, much better than I am, well, I really can't skateboard at all, but you would actually, if you were a good skateboarder, you could put energy into the system through various manipulations in your legs, and you could actually end up higher than you started. So then you can get into oscillation and not convert. But as long as you do a sort of dance thing, you could overshoot and then come back, you'll still convert, right? But if you overshoot too much like this, then you can actually divert. So the same problem happens here. So you say, well, what I can do is pick the beta so I fall at the minimum. The problem is in multiple dimensions. Now, the best value data is different along the different dimensions. So you pick a good value for one dimension, and maybe a bad value for the other. And that's what I'm going to explain in a minute. Okay, so in any case, for this cost function, you can do the gradient. Does everybody know how to compute the gradient of quadratic expression? So you have like x times dx. You want to compute the gradient. The answer is, first of all, everybody knows what gradient is, right? It's the vector of the partial derivative of the scalar function with respect to the function. So if you work it through, this is going to work out to 2 times dx. Now, depending on your point of view, some people write it as 2 times dx. Some people write it as 2 times x transpose d. It depends on whether you feel like the gradient is a column or row vector. I actually am somewhat of a believer in making gradient a column or row vector because it's using an operator. But for these notes, I think I finally got, I pinned it down and I eventually decided to make it over to a row vector, a column vector. Okay? So, I don't know. It's probably better to make it a row vector, but I made it a column vector. In any case, this is what it is, and it's a lot like just taking the scalar derivative, like we had x squared. Right? And if you don't believe it, you can just work it out in detail. So the gradient of f then is going to be equal to 1 over sigma squared times y minus ax transpose, and then times minus a plus x transpose d. So this whole thing is going to be minus 1 over sigma squared a transpose y minus ax plus dx. And that's what I have. And then you substitute the equation to get the update equation. So I think the interesting thing here is that well, there's 2 different ways of looking at it. When you have the gradient percentage, what you do is you take the difference between y and ax. If that difference were 0, then you'd be done. you're balancing information you're providing with your kind of assumptions about what a reasonable answer are, and you balance it. And then you iterate, okay, and then, well, it's just to hopefully converge. Now, with the gradient descent, you're not necessarily guaranteed to converge because of this example I gave you where you can actually overshoot opposite. Okay, so you can rewrite this term like this, and the advantage of rewriting terms like this is that now you're having an iteration which looks like a standard linear system. How many people here have taken those two? This is the standard difference equation format where you have state times a matrix, and then new state is equal to old state times a matrix plus the average working term. Right? So you can analyze the convergence, and I'm going to do that in a minute. Okay, so now, what is A? Now, one way to get intuition in this problem is to think about what A is going to be. In a typical problem, here, I have to bring it down. Okay, in a typical problem, you have Y equals AX is solve problem you're solving. A might be like a blurring operator. You have X, and A is a matrix which contains blur function. Now, if you have a linear space invariant blurring operation, okay, then so if the linear space invariant will do some blur, okay, blurring term. What's the structure of A? Okay, now your mind will think about what we're going to do in these lectures. And now, I suddenly ask the question, and you have to go, oh my God, what was he talking about? Okay. This is the problem we're solving, right? X is the input, it's an image. The output Y is a blurred version, where this is a linear space invariant filter. But it's a matrix. What's it for? Excuse me? Oh, shoot, I just remembered something. Someone told me that I had to put this thing on or it doesn't work. I hope that this whole thing wasn't a waste. Oh my gosh. That would be really bad if no one can hear anything I said up to this point because I didn't put this microphone on. Okay. Hello out there in TV land. I hope it hasn't been really bad, okay? Okay. It's given that my brain is fundamentally flawed when it comes to these matters, it's your responsibility to remind me to put on the microphone when we come into this room, okay? Okay? Everybody put up your hands and say, I promise I'll remind you to put on the microphone, okay? Okay, anyway. Where was I? Oh, the matrix A. You were asking questions to us. Oh my gosh, the acoustics in here are absolutely horrid. You know what? Has anybody ever watched the TV show Get Smart? Okay? With Maxwell Smart in 99, and then they had a thing called the Dome of Silence. We're like having a classroom in the dome, under the Dome of Silence. Okay, could you repeat that? Yeah, it's going to be toplets, block toplets if it's an image. Okay, that's the correct answer. You get 50 points and the option of moving ahead to the bonus round. Okay, so A here is going to be toplets, block toplets because it's a linear space invariant filter. Okay, now so in that case you can get a lot of intuition into the problem as to how it works. Okay. So you take, now what happens is multiplying by the matrix A is equivalent to convolution So I'm going to write this using our standard electrical engineering certified notation, which is that we write x sub s convolved with x sub a sub s, where the star is the convolution, okay? And we subtract that from y, and then convolve with a sub minus s. So why is it we're convolving with a sub minus s instead of a sub s? It's the transpose. When you take the transpose of a linear space invariant operator that's a Toeplitz matrix, what it does is it takes the time reverse of the impulse response for the convolution. That was a long sentence, but you guys know all this, right? So transposing, so if you take a times x, that's equivalent to a sub s convolved with x sub s, okay? Assuming this is a Toeplitz operator. But if I take a transpose of x, that's equivalent to a convolved with a minus s convolved with x of s. It's really a beautiful thing, okay? So, so it's kind of nice to have this intuition. I mean, this then becomes a gradient descent operator. And actually, you can see what's going on here, because remember B, let's say that B is going to be a, this matrix B is going to be the covariance inverse, it's the precision matrix for a non-causal Gaussian Markov random field. There's a lot of people hanging out there. I just hope they're not assuming they're going to use this room. Are you guys going to use this room? Oh. You got started a little bit late. Okay, that's not good. They didn't warn me about this. Okay, all right. We may have to cut this off a little early. Oh, no wonder you're sitting there pensively. The problem is that this lecture, even if I cut it, I mean, I have this room until 6:20. Is that okay? Okay. So the intuition here is that you take x, you apply the filter, then you subtract it from y, then you apply the time reverse filter, or the space reverse filter, and you add it back. Okay, now, but you also have this term over here, which is that this is like you take the pixel and subtract the prediction from its neighbor. So this expression here is the difference between each pixel and its predicted value. So if each pixel is exactly equal to its predicted value, the random field has to be very smooth. In fact, it has to be constant. All right? So, okay. Now, just to give a little more intuition into this, let's say that this filter, the prediction filter, was 1/4, 1/4, 1/4, 1/4, right? So you're saying if I'm going to predict this center pixel, I'll take the average of its 4 neighbors, right? Oh, yeah. Okay. Thank you. I'm taking the average of the 4 neighbors. Okay. So if I did that, okay, then if I take delta s minus g of s, right? That's going to look like 1, and then minus 1/4, minus 1/4, minus 1/4, minus 1/4. Okay. Right? So, okay. So if I apply this filter to an image, I'm going to be taking the difference between the pixel and the average of its neighbors. Okay. If you took 641, no, this is 637, then I think you may recall that if you take the Laplacian of a function, right? So let's say we take the Laplacian of some function, we'll call it x, okay? in 2 dimensions, right? That really is then equivalent to I think if you take minus 1/4 or something, the Laplacian, you get exactly the same operator. Okay? So, saying that the Laplacian of x equals 0 is the same as saying that convolution with this equals 0. So saying that the Laplacian of a function is 0 is equivalent to saying that convolution of that function with this discrete operator, delta minus g of s, is equal to 0 if g of s is chosen to be this function which is the average of the neighbors. Okay? And that's sort of a typical choice for this kind of an application. So I'm just trying to give you some intuition. So do you remember where the Laplacian equation like this comes up? I think there's some people here who do have some electromagnetics background, right? That this comes up. This is the equation you saw for the electric field or the potential field in an electromagnetic problem in free space with no charge in a boundary condition, right? It's also the same kind of equation you get for a thin membrane, which would be like a bubble. Okay, and so it's the smoothest function that fills in between a boundary condition. So this is like a smoothing constraint. Oh, I see. We're almost out of time. So how much time do we have? We've got way cut off. Okay, I didn't realize that there were going to be people who were going to come in here. It's not feeling very welcoming at this point. Okay. Okay, well, I guess I'm going to just have to summarize. Okay, so you're going to read the rest of this section. In fact, I think we got through the material we were supposed to for today anyway. You're going to read the rest of this section. The convergence of the gradients that you do by, there's 2 ways of doing the convergence analysis. One is by doing an eigendecomposition of the matrices. So then you diagonalize the operator, and when you diagonalize the operator, see this is 82. When you diagonalize the operator, what happens is each mode converges independently. So the convergence of each mode just looks like an expression like this, where h here is the eigenvalue associated with this operator. The operator h is A transpose A plus sigma b. So if h is, so really you want this expression 1 minus alpha h to be small, and alpha is the step size. I get 1 more minute. So basically, ideally you pick alpha such that this expression was 0 and the mode would converge in 1 step. But the problem is that all the h's are different. So you can't pick them all to be small at the same time. And then what ends up happening is that you can read this, but essentially what happens is the condition number of the matrix becomes a determining factor, which is the ratio between the smallest and the largest eigenvalues. Please read this and go through it in detail so you understand it. And then next time I'll go through the frequency analysis of the gradient descent, okay? And I think we're just going to have to cut it off here. It's going to be a short lecture because there are people are coming in the room, and basically we have to stop. So thanks a lot. Sorry, it was a little bit of a learning experience for this particular lecture, and I'll see you next time.